just coming in.
Oh, yeah, I saw her.
I think there's also another group doing something.
Yeah.
Yeah, so the people up front.
Yeah. She did mention that she was going to be back.
So, hello everyone. I think you should use this mic. No, I'll use this mic. Hello? Oh. Okay, hello everyone. So today we will hear from Anne-Marie Strehl. She is visiting NCAR from University of Bergen, where she is a postdoc working with Shuttle Wauge. Nice, I pronounced it correctly. She did her PhD in University of Bergen as well, and now she's working on the project that is looking at the impact of the Nordic seas on the overturning of the Atlantic meridional overturning circulation. But today she is going to talk about her PhD research on 70-year perspective on water mass transformations in the Greenland Sea from thermobaric to thermal convection. So welcome, Anna, and over to you.
Yeah, thank you very much for the introduction, Rita. Yeah, I'm very happy to be here, and yeah, I would very much like to say thank you to Rita for hosting me, and yeah, it was a very nice day so far. And I would also like to thank the Strategic Research Area Climate and Energy Transition at the University of Bergen and the Rover Project, who are financing my stay here. Yes, I will talk about the Nordic seas today, specifically about the Greenland Sea. And I will bring an observational perspective into this room, which is, I think, a little bit rare because most of these talks are probably more model-based. Well, I'm pretty sure you're well aware of the global overturning circulation, and you're also well aware that it's mostly driven by density gradients. And yes, so the density gradients are strongly built up or maintained by dense water formation in the high latitudes. And you see here, this is the background color is the sea surface density, sea surface density in boreal winter. And we clearly see this very nice area up here, yes, which is clearly the densest in the boreal, in the northern hemisphere. So the dense water formation in the subpolar North Atlantic and the Nordic seas is very important for driving the AMOC, or yes, the general overturning circulation. So we are going to focus on the Nordic seas today. And so the Nordic seas consist of a couple of deep basins. One of them is the Greenland Sea, which is this one up here. And then we have this Greenland-Scotland ridge down here. Oh, I should probably use this pointer whenever I can, right? Does that work now? there, the Greenland Scotland Ridge. And the Greenland Scotland Ridge is relatively shallow compared to the deep basins and compared to, well, the deep ocean. So it kind of sets a natural barrier between the Nordic seas and the rest of the ocean. And all the dense water that forms in the Greenland Sea or in the Nordic seas in general can only contribute to the overflows or contribute to the AMOG when it's actually flowing across the Greenland Scotland Ridge. And this is what we call the overflow water. Yes. This map is showing mixed layer depth in the Nordic seas, and we see very clearly outstanding the Greenland Sea here, this spot up here, where we have by far the deepest mixed layers. And it's not only the deepest mixed layers that are forming in the Greenland Sea, but it's also the by far densest waters that are forming there. And that's one of the reasons why we are looking at the Greenland Sea. The dense water that formed in the Greenland Sea was, back in the days, far too dense to actually flow across the Greenland Scotland Ridge. It was trapped in the deep basins and just spread across the entire Nordic seas, reventilating the deep basins there. But in the recent decades, so this is approximately since 2005, we see that dense water from the Greenland Sea actually contributes to the overflows. And we are very interested in understanding this change, and this is what I'm focused on today. Why or what happened in the Greenland Sea that it does not form this deep water anymore, but that we are actually forming overflow water. Yes. We're using observations. Back in the days, we did use, or people used, these kind of observation or thermometers. This is a so-called standard deep sea reversing thermometer, and this was definitely standard in the 1950s, and it was actually used until the early 1980s. So quite a lot of the data that we are using is from reversing thermometers. Salinity was back then measured with titration. Yes, today you probably know that we are using digital thermometers, much higher data quality from there, but we can of course still use the older data as well. Yes, of course, we also have a lot of challenges going into the Greenland Sea. So this is now just zooming in into the Greenland Sea, the black shape here. The gray shape is just the outline of the Greenland Sea gyre. And you see the dots are showing the available profiles or the locations of the profiles that we have in the Greenland Sea for the different periods in time. And well, we definitely see that we have much less profiles available in the first period here, the blue dots, but they are at least pretty well equally distributed across, or not equally distributed, but they are representing the entire Greenland Sea. So we are pretty confident that the observations we are using are actually representative of the entire Greenland Sea here. And then, of course, we have much more data everywhere in the Greenland Sea in the later periods. Yes, we of course also have increase of the amount of data in time. So now I'm just focusing on this line at the very top. Here you see this, the small black lines, and they are indicating when we have profiles available in time. And we see very clearly that there is an increase, a strong increase here in 2000, and this is when the Argo program started. So since then we just have automatic vehicles sampling for us. Okay, let's get into some results now. This is now the development of temperature and over depth before 1985. And we see, well, the temperature was showing some kind of variability, but there is not really a trend there. It's pretty constant over time, pretty cold. After 1985, we see that the Greenland Sea has been warming a lot, and this warming has actually impacted the entire depth range. So it's not only the surface, but also at about 4,000 meter depths, we see a strong warming here. And then we have this particularly strong warming in the early 2000s up here, just to mention that. When you look at the salinity, development of salinity, we basically can identify three different phases. We have first a very high salinity here, which is kind of impacting the entire depth range. Then we have a phase where we have rather low salinities, the fresh period. And it's very interesting that this fresh period is actually also impacting the entire depth range. So this is not localized or kind of trapped to the surface, but it's actually the entire depth range that changed here. And afterwards, we see that we have kind of a split into upper and lower ocean, and the lower ocean became more saline already, since the 1990s, while the upper ocean stayed fresh. And then, only in the early 2000s, also the upper ocean became more saline again. we are, of course, very interested in the development of density. And so this is the overall density development. And well, we see, again, we have kind of these two different phases. One where we have a very, we have some variability, but we don't have really a trend. And then after 1985, we see this consistent decrease in density that is actually also, again, visible in the entire depth range. And you probably see very clearly that this is very strongly related to the development of temperature. So it was probably the temperature that is driving the development of density in the Greenland Sea here. And this is my first take-home message for you. The warming in the Greenland Sea led to a density reduction despite an increased salinity in the later periods. So warming was driving the development here. Okay, let's look at stratification. We again see this very, very clear separation into two different phases. First, before 1985, we have a very homogeneous, extremely weakly stratified ocean below 750 meter depth. And above that, it's mostly summer stratification because we have a clear summer bias in this data here. And then after 1985, we see this formation of the stratification maximum here in the 1990s, which sinks down or descends to about 2,000 meter depth, where it then stays pretty stable and even becomes even a bit stronger. Yeah, so we have the stratification maximum here, and now the stratification maximum is separating two water masses on top, here, where we have the Greenland Sea deep water below the stratification maximum and the Greenland Sea Arctic intermediate water on top of that. And this Greenland Sea Arctic intermediate water is this new, kind of a new water mass with properties that haven't been seen before. And this is exactly the water that now contributes to the overflows that I mentioned before. Okay, so obvious question, why did this stratification maximum form? What happened here? And in order to do that, we look into a TS diagram. I'm pretty sure you're mostly familiar with that. We have temperature on y-axis, salinity on the x-axis. And then the gray lines here are isopycnals. And yes, I just want to highlight this specific isopycnal, the 30.448, which separates intermediate water from deep water. This is potential density reference to 500 meter, in case anybody cares. Okay, so these are approximately the locations of the deep water that we see in the Greenland Sea. Yeah, pretty confined over the entire 70 years, changing as well, but we don't care about this now. And when we now look at the mixed layer properties compared to this deep water, we see that at least in the very early period, 1955 to 1975, the properties of the mixed layers are extremely similar to the properties of the deep water, and they are clearly denser than this 30.448 isopycnal, so we can pretty confidently say that we are actually forming deep water here. In 1975 to 1985, the mixed layer properties are a little bit fresher and a little bit colder. And in this period, we do form both. So some winters, we do actually form deep water. Some winters, we do form intermediate water. Afterwards, we have a period where we have very low salinity. And we see that even if we would cool down these mixed layers to freezing temperature, we would not be able to form deep water anymore. And this is exactly the period when the stratification maximum formed. So we can conclude that the stratification maximum formed due to freshening, which prevented the formation of dense water, deep water in the first place. Okay, what happened afterwards? We see now we have a strong increase in salinity again. And if we would actually cool down this water mass enough, we would be able to form deep water again. So it could technically be possible to actually remove the stratification maximum again, but the increase in temperature prevents that, so we stay in the formation of intermediate water here. So the warming maintained the stratification maximum here. And afterwards, we see a development towards even higher salinities, but also to much higher temperatures. And we see that the density difference is now larger, which means that the stratification maximum is actually strengthening. And this is exactly what we saw before. Yes. Okay, so my second take-home message for you is the warming maintained and strengthened the stratification maximum, which was originally formed or initiated by the freshening event. Okay, so this is my favorite topic, I think. This is showing mixed layer depth over time. And we see a very interesting period here, 1965 to 1985, where we have outstandingly deep mixed layers that are actually bottom-reaching mixed layers. And the question that we are asking here is, what facilitated bottom-reaching convection? Why did it happen only in this period? And in order to explain this, I will quickly introduce the thermobaric effect. I'm pretty sure you've heard about it, but maybe you don't remember. So thermobaric effect says that cold water is more compressible than warm water. So if we now take two water parcels, one of them is colder and the other one is a bit warmer, and we move both of them down to higher pressures, the colder water parcel will be compressed more. And that means that the density of this colder water parcel increases faster with depth than the density of the warmer water parcel. And that means that there can be situations where the colder water parcel has lower density near the surface, but when we actually move this water parcel down, due to the faster density increase, the density is higher at the bottom. Yes. In general, the thermobaric effect is pretty weak, and we say it's usually important only below the so-called thermobaric depth. And for our green and sea mixing or mixed layer formation scenario now, we could, for example, imagining a scenario where we have very cold and fresh mixed layer near the surface, and as soon as this mixed layer is deep enough to actually reach the thermobaric depth, it will just become much denser and much faster denser than the environment, surrounding water around it. And therefore, it will just sink to the bottom. So as soon as we have a plume that actually manages to reach the thermobaric depth, it may just lead to bottom-reaching convection. And so we looked at the distribution of mixed layers that we have here, and we see very clearly that most of the mixed layers are actually shallower than the thermobaric depth, which is indicated by the black line here. But then we have a gap in between here where we don't have any kind of mixed layers. And then we have these bottom-reaching mixed layers down here. And I think this is probably indicating that these bottom-reaching mixed layers were actually caused by thermobaric convection, and that, yes, thermobaric convection kicks in as soon as mixed layer reaches the thermobaric depth. Yes, okay, so why did bottom-reaching convection stop then? I now laid over the thermobaric depth over the stratification plot that I showed you before. And we see that the thermobaric depth has been pretty constant, about 1,500 meter depth maybe, before 2000. And then since 2000, we see that there's a strong descent in the thermobaric depth. And this is mostly due to warming, so the thermobaric depth is depending on the temperature, so the warming here caused the descent of the thermobaric depth. And we see that since the formation of the stratification maximum, the thermobaric depth has actually always been either within or below the stratification maximum. And that means that the mixed layers that earlier could just reach the thermobaric depth and then turn over are now kind of trapped by the stratification maximum and never ever reach the thermobaric depth, and they don't get into this thermobaric convection regime. Okay, one little side story here. When we look at this little period here, we do actually see that there is the thermobaric depth is actually shallower than the stratification maximum here. And this period coincides with a period when many so-called chimneys were observed. I don't know if you've heard about chimneys, but they are very strongly rotating vortices that have a very, very weakly stratified core. And so when we just zoom into this period, this is again the background stratification with the overlaid mixed thermobaric depth here. And then we look at the chimney profiles that have been found in between. We see that they have a very, very different structure. So we see that they are very, very weakly stratified here, and that they that the stratification maximum is also moved down compared to the stratification maximum in the background. Stratification. So what we believe is that we actually did have thermobaric convection happening here, and that the thermobaric convection was kind of leading to the formation of these rotating vortices and the thermobaric convection was in the end trapped by the stratification maximum. It could not overcome this strong density barrier here. Yeah, so potentially the chimneys that were observed in the Greenland Sea in the early 2000s were kind of arrested thermobaric convection. Okay, so coming back to our main story, warming led to the cessation of bottom-reaching thermobaric convection explicitly by the descent of the thermobaric depth and implicitly by maintaining the stratification maximum. Okay, so we are, of course, very interested in dense water formation in general. And the question that I'm asking now is, how do changes in properties impact dense water formation? So I go back to our TS diagram, and now I'm taking two different water parcels, if you want so. And we see that both of them have the same initial density, they just have different properties. So one of them is cold and fresh, and the other one is warm and saline. And now we apply some cooling to them, the same cooling to both of them, and look at the change in density. And we actually see that the warm and saline water parcel has a much, much stronger density increase due to cooling than the cold and fresh water parcel with the same cooling. So that's quite a big difference. We can, of course, do exactly the same with change in salinity, increase the salinity here. And we see, well, there's still a difference. It's not as clear. In this case, it's the cold and fresh water parcel that has a stronger density increase. So we can take home from this, there's warmer and more saline properties lead to generally more temperature stratified oceans, and that means that they are generally more sensitive to heat forcing. So what does that mean? So we can measure this kind of stratification control, what we call it, with the stratification control index, where negative numbers say that we have salinity stratified ocean, and positive numbers are temperature stratified oceans, indicated by the colors, respectively. So let's look at the development in the Greenland Sea here. So now I show the seasonal cycle of this stratification control index for the period before 2000, so this is 20 years before 2000. And we basically see that the stratification control has been very, very stable over the years. So we don't see, this is now a bit difficult here. Yeah, we see it has basically been salinity stratified throughout the year. And when we look at the second period after 2000, we now see a very, very clear seasonal cycle here. So we have temperature stratified ocean in summer and rather salinity stratified ocean in winter. So when we now look at the buoyancy frequency, which is telling us the development of stratification over time, we see that in the earlier period, we have very strong summer stratification as expected, and then basically our convection is happening here in February and March. And in the newer period, we see we have exactly the same strong summer stratification here, but then we see that the onset of convection is much earlier, already in like October, November, and we have much more gradual convection than we had before. So this change from a salinity stratified ocean to a temperature stratified ocean in summer led to a change in the behavior or in the response of the ocean to thermal forcing. Okay, let's look at the Nordic seas for this. So this is again a stratification control index, now spatially mapped for the Nordic seas in the earlier period and in the later period. And we see the change is strongest in the Greenland Sea up here. And that's, of course, why we picked this region, right? But in general, we see that the entire interior Nordic seas have become more temperature stratified. And that means that they are generally more sensitive to heat forcing, and that means that cooling is, in general, more effective at forming dense water now than it was before. Okay, so warming increased the sensitivity of dense water formation to cooling. I've talked a lot about warming for now. Yes, I should probably also point out the role of salinity a little bit more here. We've seen that we have multi-decadal variability of salinity, but we also saw that the long-term trend of density was dominated by a temperature trend. But what we also see is that variability in salinity may cause transitions to different states of stratification. So in this case, I refer, for example, to this freshening event in the 1980s that caused the formation of the stratification maximum. So variability in salinity may trigger different states of stratification and then different states of ocean behavior afterwards. Okay, so we now have pretty much understood what happened in the Greenland Sea, I think. The question is, of course, why do we care? Does it matter? And if we want to understand where it matters else, we need to understand why did we have these changes. And well, so in this picture, you can see the three different climate components that could impact this. We have the atmosphere. This is very nicely shown by these cloud streets here that are very typical for colder outbreaks in the north. Then we have sea ice, which of course impacts the exchange of energy between the ocean and the atmosphere. And then we have the ocean itself. So we can have changes in the ocean properties due to transports or whatever. I will start with sea ice here. These are sea ice patterns that we have found objectively with using a self-organizing map based on February sea ice extent. And we see these three different patterns of the sea ice edge here, the marginal ice zone here. First, we have the large ice extent. Then afterwards, we have, and during the large ice extent, we have basically the entire Greenland Sea is covered by sea ice. Then we have the Odden pattern, where we have a partial coverage of this Greenland Sea. And then we have the open ocean pattern, where the Greenland Sea is basically ice-free. And, well, you've probably guessed this already. There is a temporal alignment to them. There's a very clear trend from the Greenland Sea being entirely ice-covered via the Odden as a transitional state towards the open ocean conditions in the latest period. So the question is, of course, what caused the ice edge retreat? Was it reduced atmospheric forcing, or was it a warmer ocean here? We look first at the total heat loss in the Greenland Sea, and we see that the heat loss is actually increasing over time. This is very strongly correlated with total ice-free area as well. So we basically see that the more ice-free area we have, the more heat we can extract from the ocean. But yeah, so since we have more heat loss in total, I don't believe that the changes in the atmospheric forcing actually caused the sea ice edge retreat here. So the other candidate is then transports in the ocean. And for that, I will just quickly introduce the boundary current system in the Nordic seas, where we have the two branches of the Norwegian Atlantic current that are transporting warm and saline Atlantic origin water into the Greenland Sea, or not only into the Greenland Sea, they bring it everywhere. And then we have, on the other side, the East Greenland current transporting cold and fresh polar water from the Arctic Ocean southward. And so for the trend towards warmer and more saline conditions in the Greenland Sea, we are, of course, especially interested in the Atlantic water component that enters the Greenland Sea. So we just plotted the Atlantic water development of Atlantic water properties in the Greenland Sea here in black, and compared this to the development of the mixed layer properties that I've shown you before. So this blue line here is showing the mixed layer development as we've seen it before, and we see that it resembles pretty much the development of the Atlantic water properties. We see we have freshening at the same time. We have warming and salinity increase at the same time. So basically, the development in the Greenland Sea has mostly been driven by changes in the Atlantic water properties that enter the Greenland Sea. Perfect. So we now know that warming in the Greenland Sea was caused by warming of the Atlantic origin water. And that means that the results that we found in the Greenland Sea actually apply to all regions that are impacted by these changes in the Atlantic origin water. And that includes, of course, the other half of the Nordic seas, that includes the Arctic Ocean, that includes the Barents Sea. So I think this is pretty relevant. Okay, we may speculate a little bit about implications for overturning circulation. And so I guess we agree that we can expect a further increase in temperature over time, and that will probably mean that we will have a further density reduction in the Greenland Sea or in Nordic seas in the future. And this may cause two different scenarios. Either we have a reduction of the density in the overflow water with the consequences that we actually don't know yet entirely, or we actually have the origin of the overflow water moves further to the north into the Arctic Ocean, when we actually start forming dense water there as well. And the second question is, of course, whether the Nordic Sea's overturning will be stable in the future, or whether it will decline or maybe even increase. And so at least from this work, we've seen that a larger open ocean area may contribute to actually more dense water formation because just we have, well, more exchange, more area that is available for exchange with the atmosphere. And we also saw that we have increased sensitivity to cooling due to the warming ocean. So these are at least two kind of, hopes that may lead to a stabilization of the overturning in the Nordic Seas. And that's actually the reason, so to answer this question, I'm here. That's the reason why we are now setting up the model to figure out what is the answer to this question. Okay, I'm trying to summarize this in kind of three main take-home messages. The prevalent warming trend across the Nordic Seas has manifested a shift toward lower densities. The associated shift from salinity to temperature-dominated stratification increased the ocean's response to cooling, and the ocean warming has driven changes in the sea ice extent and consequently the atmospheric forcing. So all these changes were mostly driven by the ocean. Yeah. Thank you very much. That's it.
Nice, brilliant. Thank you, Anna. Questions? Do I need to bring the mic or? Okay. Go for it.
Thank you for that presentation. I wanted to ask, one of the in that first part, you showed us the mixed layer depth salinities and how they got much fresher. So there's like a freshening event. And I'm wondering, I was trying to figure out like what is driving this freshening event. Was it the retreat of the sea ice and then you have kind of like a fresh water? So as that sea ice melts, then you're getting freshwater input there, or like, do you have any idea what was driving that specific change?
Yeah, it's probably related to the great salinity anomaly, and this is basically what I've tried to say in this development here. Where we see that the development here is very much following the development of the Atlantic origin water. And so what's very interesting actually is that these great salinity anomalies, at least some of them, they originate in the Arctic Ocean and then they somehow manage to go past the Nordic Seas without impacting the Nordic Seas. They go around the Labrador Sea, around the subpolar North Atlantic, come back into the Nordic Seas, and then they enter the Greenland Sea together with the Atlantic water here. So probably most of this fresh water is actually trapped on the East Greenland shelf and in the East Greenland current, and then is, well, impacting whatever happens afterwards when it's kind of re-entering with the Atlantic water. Yes, I guess sea ice, changes in sea ice may have impacted that as well. I assume that I actually think it's the opposite. So I think we first had the freshening, and because of that, we still had the formation of the Odden that we saw before, kind of this weirdly shaped ice feature there. That's my answer. Thanks. Dan?
Thanks. It was fun to learn or relearn about some of these things. I was wondering, so you mentioned about the implications, some of these changes are coming from Atlantic water, and so other deep water formations regions could be susceptible to them. I was wondering if you could talk about this. It seems like, here there's this co-location between this thermobaric threshold and kind of the places where deep water has been formed in previous decades, and that a small shift in the thermobaric threshold could have a large impact on whether or not you get deep water penetrating all the way down. Are other regions like that as well? Also, is there any control on why these things might be like kind of closely aligned?
So actually the Greenland Sea is pretty unique in terms of thermobaric convection. So it's Greenland Sea and Weddell Sea, and then I think there was one other location that is kind of known for thermobaric convection. Within the Nordic Seas is certainly only the Greenland Sea where we see indications of that, and that's also what leads, or at least back in the days, led to this very, very clear distribution of mixed layer depths, that we have the by far deepest mixed layers in the Greenland Sea, and everywhere else it's maybe 200-300 meters deep and not more than that. Now I forgot the second part of the question.
I was just wondering if there's any reason why those things may have been like so close.
You mean why the stratification maximum was so close to the thermobaric depths?
Yes.
I haven't thought about that.
I don't think so. So I think that the stratification maximum is located there because everything, so the Greenland Sea is of course feeding whatever is happening around as well. So the Greenland Sea has always exported water into the other deep basins, Norwegian Basin, Arctic Ocean, or Eurasian Basin and stuff. And so the threshold where the stratification maximum is located now is basically where the bathymetry is trapping the basin. So that's basically just the deep water that is still trapped there, that is still remnant from back then. Yes, so I think that is, it's a funny coincidence, but I don't think they are related. Yeah. Peter?
So you talked about the Atlantic water coming in that's got a lot warmer, but what's happened to its salinity?
Yes, so the salinity of the Atlantic water has also undergone these kind of, I mean, we see it here a little bit that we have first this freshening period and then since then a lot of salinity increase. After 2020, we actually saw a kind of freshening event again that is now fading out. And probably this freshening event also led to some kind of changes in stratification. We haven't looked very much into that data yet, especially not for the Greenland Sea. But yeah, so there is variability there. And the Atlantic water is generally very strongly impacted by these great salinity anomalies that are going around the subpolar North Atlantic. So salinity does not show a consistent trend, it's just showing some kind of oscillations, decadal oscillations, maybe even multi-decadal oscillations.
So what causes these great salinity anomalies?
Good question. Yes. Okay, so we have, so the ones that are originating in the Arctic Ocean are usually believed to be caused by this Beaufort gyre thing. So I think there are some wind events that cause weakening of the Beaufort gyre and therefore it kind of just releases all its fresh water. I don't remember what exactly causes this, but yeah, Beaufort gyre stuff. Some other of the Greenland Sea great salinity anomalies are actually originating in further south. So there was one that was actually caused by fresh meltwater. I think there was meltwater from the Greenland ice sheet. That was at least involved in the latest one in the 2010s. And then we also had one that was somewhere close in Hudson Bay. I forgot the reason for that, but it had kind of a different origin, but was also leading to a lower salinity in the Labrador Basin afterwards. And then we had one that was caused by some winds, extreme events or changes in extreme winds around the tip of Greenland that were then causing shed off of fresh water from the kind of the shelf into the deeper ocean. So there are many different reasons for causing great salinity anomalies in the Green Sea, I think, or Nordic seas. Frank?
So, if I understood correctly, the deep part of the basin hasn't been ventilated now in 20-ish years.
That's correct.
And, well, two questions. One is, have you looked at any tracer observations to look at the age of the deep water and whether that's increasing in a consistent way with that interpretation of the TS data? And the second part of the question is related to one of your last slides about stability of the system. And do you consider reventilation of the deepest part of the basin part of the stability question, or is it expected to just sit there and go anoxic in 100 years because we will never ventilate that again?
Mm-hmm. Okay, I will go for the first question first. So I haven't looked at tracers, but other people have done that. And so what is very interesting is that we definitely see this, this long-term kind of decrease in oxygen and SF6 stuff. So definitely the tracers also indicate that we don't have ventilation of that anymore, except for actually one measurement in 2001, I believe, where some oxygen measurements indicate that there was deep convection there. We don't know if there was a false positive. We don't know, because all the other measurements don't show this kind of, don't show traces of this event. So yeah, that's a bit unclear.
But yeah, so in general, tracer observations do agree with that we don't have ventilation anymore. Tracer observations actually do indicate that the cessation of bottom ridging convection already happened a little bit earlier. They say it already happened around 1980, where we see it here from the TS properties mostly after 1985. So yeah, it may be that, for example, not the entire Greenland Sea has been ventilated anymore, or the volume of reventilation has been smaller. The second question for the stability, yes. So I don't think that we currently will have any chance to ventilate the deep ocean or the deep Nordic seas anymore. So I guess that's pretty much, well, shut down. So the stability mostly refers to formation of overflow water. So how much overflow water will we actually still form in the future, and how will this overflow water change? So will this also are we actually able to maintain the density because we are, for example, increasing the salinity sufficiently? Or what happens if the density decreases, and by how much, and so on? So yeah, I guess that's more the stability question here.
Okay. I had a sea ice question again. So how much of the sea ice is just formed locally in the Greenland Sea? Is there anything that peels off the East Greenland current and gets out into the deep Greenland Sea?
Yes. So we see there a very, very clear transition as well. So in the older days when we had the full coverage of the Greenland Sea, it was mostly actually locally formed sea ice. The Odden shows a very nice transition, because in the beginning it was also locally formed, but later on we see it's mostly actually sea ice that is transported into the Greenland Sea with this Jan Mayen current that branches off this Greenland current. So it's actually both. Yeah.
Ben?
One more question. So yeah, you motivated this work with this picture of a water mass that had been confined regionally and then was kind of leaking out. And I guess I'm wondering about like what the implications are for the overall overturning, if overturning is changed in this particular place. I mean, I guess a question first is like, can you talk a little bit about the net export of waters from this place, if the mechanism of that is changing? And then also, maybe there's less overflow water, but is there a possibility these things could be recirculated and maybe precondition convection in other regions?
Yes. Okay, that's a pretty cool question. So that's exactly what our project is about now, kind of. So what happened in the past is that we already, I don't think I have the figure here, no. But so this is a result from the Huang study that I showed in the beginning, where they showed that kind of the Greenland Sea started to contribute to the overflows. And they also see that before 2005, it was kind of the rim of the Greenland Sea and the Iceland Sea who mostly contributed. And now after 2005, so since we have the formation of this new water mass that is less dense, it's actually the core of the Greenland Sea that contributes to the overflows. So we definitely see a regional change in kind of which region does contribute to the overflows now. We know that the variability in the overflows is mostly driven by variability that is kind of happening to the boundary current system. So we do have a lot of preconditioning or a lot of dense water formation already in the boundary current system. And at some point, the boundary current is just kind of either below a layer of cold and fresh polar surface water or below ice, and then it isn't transformed anymore. So it's kind of, so the most of the boundary current transformation happens kind of in the Norwegian half of the system, and the variability of the transformation in the boundary current system leads to variability in the overflows in the end. So the contribution from the basins is pretty stable, and that's probably because actually we have this kind of integrative effect, that we have water that is kind of pretty long localized in the interior basins, especially the Greenland Sea, and there it can just integrate its dense water formation over a couple of years. Well, I think it's definitely not longer than 3-4 years. That's the typical residence time, I would guess. And so the hypothesis for our future is that because of the ice at retreat, probably the East Greenland current is also becoming ice-free at some point. So potentially the East Greenland current is actually opening for more dense water formation in this current, such that we actually have a larger contribution from the boundary current system. But yeah, that's open to research. Yeah.
Nice, thank you. Do we have any questions online? Question, no evidence that runoff from Greenland is increasing now?
Okay, so I don't know anything about the Greenland ice sheet, to be honest. So we don't see that runoff from the Greenland ice sheet is impacting the Greenland Sea in any way, except for if it's actually entering the subpolar North Atlantic and then kind of re-entering the Atlantic water, the Nordic seas. But that's, I think it's extremely difficult to clearly relate this to a specific runoff event or something like this, because there's so much smoothing along the way, that there are so many possible causes for changes in salinity further upstream or downstream, whatever. That it's basically not, we can't say if the Greenland Sea runoff, Greenland ice sheet runoff is contributing to trends there.
Okay, nice. Any more questions online? No, that's it.
I have one more.
Go for it.
So you're visiting here. Is there any evidence that the models are showing these similar trends and effects?
I don't know. I have so far only looked at observations. So so now I guess you're more asking about kind of the East Greenland current contributing to net water formation in the future. We are investigating this. We have 2 PhD students who are looking at this now. We don't know. And what we are trying to figure out now is actually if we have changes in the Nordic seas, how will this impact AMOC further downstream? But yeah, I guess in a year or 2 from now, I will be able to tell you more.
Yeah, she'll come again and report.
Yes.
Yeah, but it was my question too, because I was also curious whether like this maximum in stratification, like whether it's captured in, I don't know, like ECHO, GLORIS, or like any other ocean reanalysis or not.
Yeah, it's actually not. So in reanalysis, we haven't, so at least I haven't, I can't recall anybody actually seeing this. So we have had a master student looking at this. But I think she was like, well, the stratification is actually pretty bad here. And so I've looked into the E3SM that they are developing in Los Alamos. And well, I gave up on this because we couldn't see these changes in stratification. We wanted to use the model to actually investigate where the stratification changes come from. But yeah, we weren't able to find it there, and therefore we gave up on that project.
Yeah. Okay.
And your earlier slide that the evolution of the observing system, it seemed like there were transitions in the observing system which match up pretty closely with transitions in the characteristics of the Greenland Sea. I wonder, has anybody looked into whether that's just a coincidence or whether there could be some kind of misrepresentation of what's happening?
So you mean kind of these figures here?
It's very close to the beginning.
Yeah.
Yeah, that shows part of it. But
Yes, this one, for example.
like around 2000, the Argo floats start.
Yes, so I mean, so the changes that we see here are mostly due to changes in gridding. So of course we have, I've spent so much time on gridding this data properly and looking into kind of outliers of data. So I'm pretty sure that the data that the results that we see here is actually realistic and representing what happened. So the changes that we see here is that because I have a grid that is first having, I think, 6 monthly resolution and then a bi-monthly resolution and then afterwards a daily resolution or weekly resolution or something like this. So basically that's where we do see these the seasonal cycle here that we don't see before, because here it's basically just smoothed out by the grading process. And I mean, we definitely have a clear bias in earlier data towards summer data. So we see, that's probably very difficult to see for you, but these black lines here are overlaid on top of white and red stripes. And so most of them are located within red stripes, which indicate summer. So most of the data we had back then is from summer, which makes a lot of sense because nobody wants to be in the Greenland Sea in winter. And yeah, so the Argo floats basically allow us to see the very clear seasonal cycle here. But the changes in the deep water should not have a very, very clear seasonal cycle. I mean, obviously we do want to have bottom-reaching convection, but we have, for example, I mean, the bottom-reaching convection profile that we saw here are from May, mostly April and May, so late winter already. So they are showing remnants of this bottom-reaching convection mostly. Yeah.
Alice? I guess along those lines, have you like subsampled the post-Argo period and just looked at summer or something? And does it affect the, maybe the overall trend is still negative, but does it affect like the magnitude of the trend or anything like that?
I did look at this, but it didn't have any changes.
So are these plots an area average over the Greenland Sea? Is that what?
Yes, correct. They are including all profiles that are within the black contour.
Yeah.
Yes. So I've also subsampled the different regions here. So I've I think I've made 4 different parts of the Greenland Sea and seen if they are kind of developing in the same way or if they are very different, and they do basically do exactly the same, except for that maybe this region up here may be slightly fresher than the rest, which is mostly because we have more more effect from the East Greenland current here. But yeah, so they do show the same overall behavior. They do show the same periods in terms of high salinity, low salinity, high salinity, and also the kind of separation into the upper and lower ocean. So I think that these plots are actually very representative of what happened.
That's okay. Any more questions? Anything online or no? Okay. If not, then thanks.
Similar to what you looked at.
Oh, yeah, just landing in a conversation with Bergen.